Well, but that was the easy one, the easy exam. Yeah, well, there's the second one and then the final. Yeah. So no, it's not cumulative. The exam two is just whatever we cover. Okay, so so yeah, we're gonna start chapter 4, the polynomial functions. Okay, so this is probably a completely new topic. Everything we've done so far you might have seen before at some point or the other. Some of you knew about imaginary numbers, some of you knew many things, but this is pretty much um, new. Okay. Now we understand what a polynomial is in general, but now we're going to define it precisely and introduce a whole bunch of little terms. So a polynomial function, so definition of a polynomial function is a function of the form, and I'm going to write it down. You just copy it over, and then I'll talk about what it all looks like, because it's going to look a little scary, but it is, and it is a sub n x to the power n plus a sub n minus 1 x to the power n minus 1 plus, we can keep going like that, all the way to, just write it down and I'll tell you what all that nonsense means. So every time you see a letter with a subscript, like this thing right here, a sub n, all it means is just some real number. And that little subscript doesn't carry any mathematical meaning, just to say that, a sub n is probably different from a sub n minus 1. It's just the way to distinguish constants. All it is, they're just constants. Well, where n is a natural number. So let's label a few things. So n is a natural number. So all those a's with subscripts, so all those a sub i's are real numbers. Okay, so you have a number, variable, exponent, number, variable, exponent type of situation. So you've seen those functions before. We're just putting a little precision on it. What? Okay. Um, so you just have those real coefficients. Now, a little bit of terminology. Whatever the highest power that you see, in this case it's n will be the highest power, that determines the degree of this polynomial. So we say this is a polynomial of degree n. So if the highest power that you see is 5, it's a 5th degree polynomial. If the highest power that you see is 11, that's the 11th degree polynomial. This first term that carries the highest exponent, the a sub n x to the n, we call it the initial term. The constant itself, a sub n, is called initial coefficient. So whatever the highest power you see, that's going to be the degree. Okay? So initial coefficient. And that last number in the end, the one that does not have an x, the a sub 0, is called the constant term. So this is just verbiage, just a bunch of little definitions. So if I just give you an example of a function, let's say f of x equals negative 3x to the power 5 plus 11x squared minus 7x plus 2, something like that, that would be an example of a polynomial function. So all you're looking for, that exponents are positive integers. There are no variables in the denominators. So things that look pretty. Okay? Does that make sense? So no fractional exponents, no negative exponents, positive integer exponents. Okay? Now, can you tell me the degree of this polynomial? Yep. So it's a 5th degree polynomial. So right, this is a 5th degree polynomial. What is the leading coefficient? Yeah, negative 3. The constant in front of your highest exponent is the leading coefficient. Yeah, I should say, sometimes it's called leading term or leading coefficient. So the leading coefficient is negative 3. Yeah.
Okay, so for a sub n, xn is initial term, we want to call that as initial coefficient. So these just happen to be the same? Or is there what's the difference between the initial coefficient and the leading one?
Well, the term carries the x,
Okay.
and the coefficient does not. So the coefficient is just the constant, while the term carries the variable as well. So the leading term here, so the leading term is negative 3x to the power 5. Okay? So usually when we say coefficient, that just implies that you're looking at a constant. Okay? So yeah, your book actually uses the leading term and the leading coefficient language. Sometimes you hear initial, but so we're just going to call it leading from now on. What is the constant term here? 2. So the constant term is that okay? So again, the highest degree determines, the highest exponent determines the degree of the polynomial. The highest exponent with the constant, that's your leading term. The constant in front, that's your leading coefficient. Okay? So it's all about the highest exponent. It's not the order in which things are written. Because if I rearrange the way I write terms in this polynomial, it won't affect what my degree is, the leading coefficient, leading term is. Because it's all connects to the highest degree. So what I mean by that, if I write this example, let's say 11x, okay, that's 11 somehow. 11x minus 4x cubed plus 12x squared. That is a 3rd degree polynomial because you just focus on the highest exponent. What would be the leading term here? Negative 4x cubed, and the leading coefficient is negative 4. So it's not whatever's first, it's whatever attached to the highest power. And those are really, little technicalities, but on your homework you'll be asked, A, what is the leading term? So you have to make sure it goes with the highest exponent. So the constant term would be 0 in this case, okay? Yeah, on the last one we had 2, but here we don't have a number with an x, without an x, so we assume it's 0. Okay, so you're right. So that's a 3rd degree polynomial. So the leading term is negative 4x cubed. The leading coefficient is negative 4. And the constant term is 0. Is that okay? All right. Now, the reason why we talk about this definitions is that that leading term and the leading coefficient, but that whole term right there tells us a lot about what the graph of this function is going to look like. Okay? It will actually tell us in the long run what the general shape of a polynomial graph would look like. So we're spending a lot of time just looking at that. That leading term. Okay. Now, so about the graphs. The graphs of polynomial functions are pretty smooth and just very friendly. Okay. So the graphs are very friendly. Okay. They are pleasant to look at, and they're all fun to draw. So we'll be doing a lot of that. Okay? You ready for that? We'll do a lot of silly graphing. But I'm going to start, let me just talk for a little bit. Don't write anything down. I might be writing stuff here, but I don't want you to write anything down. So let me give you an example of a function. F of x equals, I don't know, x to the power 5 minus 3x squared plus 11x minus 2. Okay? So that's a fifth degree polynomial, odd degree polynomial, right? We can also say that. So it's a fifth degree, so it's an odd degree polynomial. But let me ask you this question. What happens to the values of this function as x gets bigger and bigger and bigger and bigger? If I start plugging in big numbers in for x, what will happen to the total value of this function? What do you think? Well, not exponential, but it will increase. You're right. Okay? And the junk that follows our leading term won't even matter after a while, because when I get x large enough, those terms, I mean, yeah, they'll affect the value of the function a little bit, but not by so much that it will, make the function turn. It will just keep going up. What I mean by that, if I plug in 1,000 in for x, right? What is 1,000 to the power 5? How many zeros is that? 15 zeros, right? So trillion is 12 zeros. So what's after trillion? So whatever that thing that comes after trillion, right? So let's say you happen to have that much in your banking account, that thing that comes after trillion. But when you're just squaring 1,000, that's 6 zeros. That's just a million, right? So if you have $1,000 trillion and you just dropped 3 million out of that, would you even notice that? Is that going to make you cry? It's just a, it's a little drop in the, in the sea, ocean of stuff. So this function really behaves just like x to the power 5 in the long run. For extreme values of x. Don't write this down. I'm going to make it official. I'm just talking still. And by extreme values, I mean very large values of x, so very small values of x. If I plug in negative 1,000 in there, I'll get a really, really big negative number, right? And all the junk that follows it won't affect the fact that I'm going to get a really, really big negative number. Just like just x to the power 5, it will look like that. If right? X to the power 5 looks like that, just like an x cubed. Well, this function in the long run will look like that. Some things will happen in the middle, which we'll figure out a little later. But in the long run, it will go up on the right and down on the left. So all odd degree polynomials will look like a basic cubic function in the long run. It was going to go up on one end and down on the other end. While all even degree polynomials will look like parabolas in the long run. It's going to go up on both ends. With some junk happening in the middle, we'll figure out that junk later. But in the long run, all the even ones are going to go up or down, depending on the sign of the leading coefficient. So this is what you should write down. We're going to make a little table. I'm going to call this the end behavior, or the leading term test. It tells us what the general shape of a function is going to look like. So I'm going to make a little table. Now I'm going to make a little table like that. Here I'm going to say n is even, n is odd, and here I'm going to say the leading coefficient is positive and the leading coefficient is negative. So just those two things will help us to determine what the shape of the graph is going to look like. Because if I look, I'll give you a second till you write that down. So in the long run, again, we're just talking about the end behavior, what happens on the tails of a graph. If your function is, if a polynomial is of even degree, in the long run, it's going to just look like a parabola. It's going to go up on both ends. So if the leading coefficient is positive and the degree is even, it will look like a parabola in the long run. Something will happen in the middle, I don't care yet. We'll figure out the middle later. But at least we know in the long run, it will look like that. Just like a parabola with a positive number in front of it. If you have a negative leading coefficient, what does the negative in the front does to a graph? Yeah, upside down. So just like an upside down parabola, it will go down on both ends. With something happening in the middle, which I don't know exactly what's going to happen in the middle. We'll figure that one out later. But in the long run, all even degree polynomials will follow the general parabola shape. Okay? So it's either going up on both ends or going down on both ends, depending on the sign of the leading coefficient. And at the same time, if n is odd, it's just going to look like a cubic. Okay, so if n is odd, if you have an odd degree polynomial, so it will look something like that. Positive leading coefficient, so just like a cubic function. And if you have a negative leading coefficient, it will look like that. Does that make sense? So again, in the long run, for extreme values of your variable, when x is very, very big or when x is very, very small. There's another way to describe this behavior, so we can put some mathematical words to that. Like, for example, this tail right here, I can say that the values of the function go to infinity as values of the x get large, right? That's what's happening. As you make your x bigger and bigger and bigger, the values of the function fly to infinity. So I can say this, f of x goes to infinity. This is the official notation. You have kind of an arrow pointing. So f of x goes to infinity as x itself goes to infinity, right? This end values of the function go up as x gets higher, right? How would you describe this tail right here? What happens to the values of the function? Yeah, f of x goes to negative infinity as x goes to infinity, right? This tail right here, I can say f of x goes to infinity as x goes to negative infinity. As x values get smaller and smaller, the value of the function gets bigger and bigger. Is that okay? And of course I can label all, what is it, 8 of those tails. I'm not going to do that. I think that should make sense. So let me just give you an example. I'm just going to give you a polynomial function, and we're just going to state the end behavior, what's going to happen in the long run. And that's it. We're not going to go any further. But any questions on that so far? Does that make sense? If you just remember, all even behave like parabolas and all odd behave like cubics, that's all you really need here. Okay? And then you understand what a negative sign in front does. It just flips everything. So, for example, if I give you this function, f of x equals 2x to the power 5 minus 3x plus 1, can we state the end behavior? What's going to happen in the long run? How would you describe that? We can just do it by a quick picture. Yeah, so it's an odd degree polynomial, so it's going to look like a cubic. It's going to go up on that end and down on that end. Again, in the middle, I don't know. So we'll fill in the middle later. Or you can say this, f of x goes to infinity as x goes to infinity, and f of x goes to negative infinity as x goes to negative infinity. That's a sloppy infinity thing there at the end. Is that okay? Happy? So that's the easy part, to determine how the graph of a function is going to behave in the long run. But it's kind of an important thing, because if I tell you a few more dots along the path of this graph, you'll be able to connect them and have a pretty picture going on for you. Okay? So I'm going to give you this statement, and this statement we'll focus on that statement for a couple of weeks. That's really going to be a driving force of everything that we're trying to do here, which we basically all we're trying to do is to learn how to factor polynomials regardless of how messy they are. Okay? Because so far you can factor a very limited amount of polynomial functions, right? You can do your trinomials when it's nice and pretty. You can do maybe 4 terms by grouping. At least you tried on that test, right? But if I just give you a polynomial that has like 7 terms and I ask you to factor that and it has like an 8th power, might not work out as smoothly. But we're going to try to factor everything that comes across. Yeah, that's the whole real thing here. So I'm going to give you this statement. Actually, there are 4 statements. So the following four statements are equivalent. What that means, if you have one out of those 4 statements, you have all 4. That's what it means equivalent. One implies the other and so forth. So first of all, let p of x be a polynomial function. So the first statement, x equals a is a 0 of p of x. Now, we've defined a 0 of a function before, okay? And basically, all that means, if I plug in a into my function, I'll get 0 out of it. That's what it means for something to be 0. So that's equivalent to saying that p of a equals 0. That's the definition of a 0 of a function, okay? So that means, what is the y value when I plug in a for x? 0, right? So that means that x equals a is an x-intercept. Of the graph y equals p of x. Right? Because a makes my function equal 0. That means it hits the x-axis at those points. Is that okay? Kind of? Third statement is still based on the fact that a is a 0 of a polynomial, so x equals a is a solution to equation p of x equals 0. What do you think of that statement? Right? I mean, when I'm trying to solve an equation, p of x equals 0, I'm looking for values of x that will make everything equal 0. Well, that's precisely what a does. A turns my function into 0. So this 3, are you okay with them? Do you see how one implies the other and intertwined? So we're happy with this. Bam, bam, bam. We're good. We see how one is equivalent to the other and so forth. Now I'm going to give you the fourth statement, which feels good. And we kind of used it once on a very, well, we used it once, and you didn't like it. And I never really hold you back to that moment. But x minus a is a factor of this function. Now this one is a little harder to see. We can see that if x minus a is a factor, then all those other will work. Because if x minus a is a factor, and then x equals a is one of the solutions to this equation, and so forth. But the other way around is harder to see. And we use that, remember that problem, you know, if you have a quadratic function that has x-intercepts, -2 and +5, find that function. We did that exactly a week ago in class. So yeah, that was what we're kind of talking about. But anyway, so we'll talk about this statement in more detail a little later. But for now, we're almost happy. Are we almost happy? Do we almost see how they all mean the same thing? Do you all understand what I mean by saying that they all mean the same thing? Yeah? The equivalency, if you have one, you have all four, right? And basically, what I have to, and we were happy with the first three. With this one, let me show you this. Don't write this down, but I can prove, let's say, if x minus a is a factor, then x equals a is a 0, that's easy to prove. Because if x minus a is a factor of my polynomial, that I can write p of x as x minus a times whatever. That's what it means for something to be a factor, right? Well, if I want to find a 0, I have to set it equal to 0 and solve for x. So it's either x minus a equals 0 or whatever equals 0. So x equals a. So x equals a is one of the zeros, right? So I got 4 implied 1, and then I got the rest, okay? So that's easy. Going the other way around is hard, because I also have to show if x equals a is a 0, then x minus a is a factor, and that one we need to slow down and maybe wait a day or two to prove. But that's kind of a big result. That will allow us to factor and solve equations and things like that. But it is true. I don't have enough tools to show you yet, okay? But for now, remember that these 4 things mean really the same thing. One implies the other. If you have one of those statements, you have all 4, okay? And that's really important. And I'll keep bringing this up, and I'll drive you crazy with these 4 statements. The whole chapter 4 is kind of based on that we understand this 4 statements. At least that's how my head works as far as this is concerned. Is that okay? So we're going to be talking about the x-intercepts and the zeros and so forth. Now, a few quick guidelines. What's going on with this thing? A polynomial of degree n has at most n zeros. So a 7th degree polynomial can potentially have 7 different zeros. Okay? It could have 2, it could have 5, but at most 7. Cannot have more than 7. Okay? So that's one statement. Now the second statement, if it has at most 7 zeros, how many x-intercepts can it have? 7, right? Those are the same things, right? Now try to picture this. Don't write this down. 7 x-intercepts. I don't know why I chose 7. That's a lot. But anyways, 1, 2, 3, 4, 5, 6, 7. Right? So now let me try to... So the polynomial did something like that. How many turns did it take? 1, 2, 3, 4, 5, 6. Right? To draw that picture. So an nth degree polynomial will have at most n minus 1 turning points. Has at most n minus 1 turning points. Now, again, 7th degree polynomial does not mean it will have 7 zeros. It might just have 1, but at most 7. Okay, we'll talk about all the details of that a little later. Actually, I'm not going to give you the third statement. The 2 is plenty. So any questions so far? Are you okay? I mean, I'm just giving you definitions and verbiage and things like that. Are we okay? All right. Now, let me give you this example. F of x equals 2 times x minus 1, x plus 4, and x minus 3. Let's say my polynomial is in this awesome form. It's factored. Means life is as good as it gets when things are factored. Can you tell me the degree of this polynomial? 3, right? If you pretend foiling this whole thing out, you'll get x cubed somewhere, and that will be the highest exponent. Do you agree with that? So that will be the third degree polynomial. Now, since x minus 1 is one of the factors of this polynomial, can you tell me one of the zeros of this polynomial? 1. Can you give me a few more zeros? Negative 4 and 3. Right? You can just read from here that x equals 1, x equals negative 4, and x equals positive 3 would be the zeros of this function. Therefore, positive 1, negative 4, and positive 3 are the x-intercepts of the graph of this function. Right? They all agree with that based on those 4 statements? Factor implies 0, implies intercepts, and so forth. So I can actually graph this function. At least sketch a graph of this function. Because look, it's a third degree polynomial, right? Does it have a positive or a negative leading coefficient? What do you think? Positive. So then the end behavior in the long run, it will start here and it will end over there. That's the end behavior of this polynomial. Now, the x-intercepts along the path of this graph will be negative 4, positive 1, and positive 3. Right? These are my x-intercepts. Now, can you tell me if you start on the bottom over here, right, and you have to go and connect, hit those x-intercepts? Yeah, and do you agree that there's only one way to do that? Right? There's no 2 options but go and do something like that. Do you agree with that? If we didn't have the end behavior, if we didn't know where to start, there would be 2 ways to do that, because I could have started on the top and I could have done the same thing, right? But since we knew beforehand that we have to start in this region and end in that region, there was only one way to connect the dots. How was that? Was that fun? See how things kind of... Now, we can find the y-intercept by plugging 0 in for x. That's old news, right? The y-intercept, if I put in 0, what do I get? 4 times negative 3 is negative 12 times negative 1 is positive 12 times 2. Okay, that's 24, not drawn to scale, but y-intercepts are easy. You just put 0 for x. That's your y-intercept. But as far as the x-intercepts and connecting the dots, was that all right? I know it's probably now looking very confusing, but the blue graph, that's what we started with. Right? Happy? Life is good right now, right? I know it's going to get crappy if it's not factored. Because that's the big thing, the big part. If you get it factored, then life is good. Any questions on this? Now, if you look at the examples that your book does on this stuff, they're also going to plug, they're going to plug few points, let's say between negative 4 and positive 1, to see what the graph is. That's just, to me, that's redundant. If you understand the end behavior, where's the start, where to end, and where to hit the x-axis, there's only one way to connect the dots. So the book will give you the same problem with about a page-long computation. No, we know the end behavior because of the third degree. Okay? The 2 helps us to, the only thing that 2 tells me is that it's positive. So I know it just behaves like a normal cubic. It starts here and then ends over there. Okay? All right, so good? Let me try something else. What if I do this? F of x equals 2, x minus 1, x plus 4, x minus 3 as before, but I'm going to square that one. Yeah, that's all I'm going to do. I'm just going to square that one. Okay? What is the degree of this polynomial? 4, right? Basically, you just have to count. You have 1x here, 2 here, and 1 there. So that's 4. Do you agree with that? Or just count all the exponents. If you count all the exponents, 1, 2, and 1, that'll tell you the degree of the polynomial. Is that okay? If it's factored. So that's a 4th degree. Positive leading coefficient, right? 2 is still positive. So it's going to look like a normal parabola in the long run. So it's going to do this, and it's going to do that. Now, what are my x-intercepts? Yeah. What? Oh, I don't see a positive 4. Well, let's just... Where do you see negative 2? All right, well, let's start slowly. Let's name all the factors of this polynomial. Name one of the factors. So x minus 1, that means x-intercept is 1. Name another factor. No, factor. X plus 4? Yeah, x plus 4 is one of the factors. So the x-intercept is negative 4. Right? Name another factor. All right, x plus 4 appears there twice. So what? So we're just going to, that's kind of weird. We're going to hit negative 4 twice, but it's just still same point. And then the next minus 3. So we still have negative 4 as one of the x-intercept. That didn't change from the previous example, right? My x-intercept stayed the same. So I have that negative 4, positive 1, and positive 3. But now try to connect the dots. And what? Well, how you doing that? So let me do the magic pen. So down negative 4, up 1. And I ended up in the wrong part, right? How do you do that? Yeah, you're right. So actually what will happen at negative 4, because that term is squared, basically what it's going to look like, if I just ask you, can you graph, without anything else, x plus 4 squared? What is the graph of x plus 4 squared? It's a parabola. Where is it going to sit? At negative 4. So really, it's just going to look like a parabola sitting at negative 4. It's going to come down, bounce off negative 4, then turn around and continue as planned. Okay? So if you see the even exponents on your factors, that means you're just bouncing off the x-axis. Okay? So it actually behaves like a tiny parabola there. Those guys, see, x minus 1 is a straight line, so it behaves like a straight line when it goes through 1. X minus 3 is just a linear thing, so it behaves like a linear thing when it goes through the x-axis. But the even ones, it will bounce off the x-axis, either from the top or from the bottom, depending how you approach this. But this way, we actually respect our end behavior. We start where we're supposed to start, and we end where we're supposed to end. Well, but no, it has to bounce off the one that has even power. So that even power determines the bouncy thing. Yeah, but it will be wrong then. Okay? Because in this, because again, I want to avoid us to be plugging any numbers in here. But if I take a number, let's say if I take 0, right, and I plug it into my function, I'll get something positive, right? So it has to be above the x-axis. But if I take a number to the right of 1, let's say 2, and I plug 2 into my function, see what happens. So this is, yeah, right, I just need the sign. So if I plug in 2 into the first parenthesis, that's positive, right? Second parenthesis is always positive because of the square. But this one will give me a negative if I plug in 2 for x. So positive times negative gives me negative. So it is below, right? So it's not bouncing, it goes through. But if I look at this one, if I take two numbers around -4, let's say if I take -5. By the way, you never have to do that. Your book does it for some reason, but I don't want you to, it's waste of time. If you understand the bouncy thingy. If I take -5 and I plug it in there, I'll get a negative, right? This will always be positive because of the square, and then I'll get another negative, right? And what is negative times positive times negative? Positive, so we're above the x-axis. And if I, let's say, take -3 and I plug it in there, I'll still get a minus, a plus, and a minus. You do that? So it's still positive. So it's above the x-axis on both ends of that point. So that's how you get the bouncy thing. But just remember, even powers will make the graph bounce. Okay? We're going to call that number multiplicity. So that's the multiplicity of this 0. See, I appeared there twice, so multiplicity is 2. If I had a power 11, it will have multiplicity 11. Okay, so whatever those little powers are, we call them multiplicities of those zeros. So the even multiplicity bounces, odd multiplicity goes through. Okay? Now I'm going to write this down, the definition of multiplicity. Don't rush that yet. Let me give you another example. I'm going to do the same. So what did we do? X minus 1, x plus 4, x minus 3, but then I'm going to do this. Power 4, power 3, and then power 5. Like that. Okay? So first of all, what is the degree of this polynomial? 12, right? If you were to actually open up all the parentheses, at some point you would go x to the power 4 times x to the power 3 times x to the power 5, which will give you 12. Or just, again, add all the exponents. That would be the degree of that polynomial. So the degree is 12. So it's even degree, positive coefficient, so it's still going to look like a parabola. It's going to do that. It will still have the same x-intercepts as before. It will have -4, +1, and +3 as our intercepts. Okay? So, but again, the only thing we have to remember that it will bounce off the even ones, and it will go through the odd ones. Okay? Now, when it goes through the odd ones, it actually does something funky. If you picture the cubic function, how does the cubic goes through the origin? It kind of wiggles. So all those, they're just going to wiggle through the x-axis. Every time you see odd exponents like 3 and 5, it will look like a tiny cubic. So even exponents look like tiny quadratics when they hit the x-axis. Odd exponents look like tiny cubics when they hit the x-axis. Power 1 looks like a straight line. So that's what we did before, right? When it was just power 1, it goes straight through the x-axis. But the high exponents will really behave like those parent functions. So -4 has odd multiplicity, right? It has a power 3, so it will go through, but it will go through like kind of like that. It will do a little wiggle, like a cubic function does. Then it will have to turn around and come back and hit 1. What's going to happen at 1? Bounce off, because 1 has an even power, so it will bounce off that like that. So it stays below, so it's a little upside down parabola, but it's still like a parabola. Then it'll have to turn around, and it will have to wiggle through +3 like that. So that would be the general shape of that graph. The y-intercept I really don't want to do because it's going to be very large. So that's the idea, okay? So again, if you just remember that if you picture the graph of x minus 1 to the power 4, it's just a parabola shifted 1 unit to the right. Now, whether it's upside down or not, that's just depending how you connect the dots. So all the even ones look like parabolas, all the odd ones look like cubics. If it's just 1, it goes straight through. Okay? Yeah. Question?
Does anyone besides mathematicians understand this?
I hope you understand that right now.
People who do this in their job, like do they just put it in a computer?
Oh, depending on what your job is, but the question, I was starting this conversation. Didn't we have that conversation before?
Well, I'm sincerely just interested.
No, I mean, it's,
I just I don't like doing things that I don't understand what I'm doing.
but you understand how we did that.
Yeah, now someday I'll probably doing it and be like, I don't know.
Oh, that's okay. You see, when I was 12, I was able to do a split, and that was like totally awesome back then, and that really helped me to develop some other skills in my life. But I no longer can do a split, so what? But it did help me at some point. Does that make sense? All right, that's what's going on here. Actually, let's do a little break and then we'll come back. Oh, wow, I got that one on record.